Here's a question that should keep you up at night. Will humanity ever actually leave our solar system? And I don't mean sending some tiny probe out into the void. I mean us, you, me. Future generations are actually traveling to another star system. Because right now, we're stuck. We're cosmically landlocked on this tiny blue marble, orbiting an average star, in the suburbs of an unremarkable galaxy. The nearest star to us, Proxima Centauri, is 4.24 light-years away. That's about 25 trillion miles. With our fastest spacecraft, it would take over 70,000 years to get there. 70,000 years. For context, 70,000 years ago, humans were still living in caves and hadn't even invented agriculture yet. But here's the thing, humans are stubborn. We're ridiculously ambitious. We went from the first powered flight to landing on the moon in just 66 years. We've sent spacecraft to every planet in our solar system. We've already sent 5 objects on trajectories that will eventually leave our solar system entirely. So the question isn't really, will we ever leave? It's how soon and how far. Over the next 40 minutes, we're going to dive deep. We'll look at the insane physics problems we need to solve, the wild technologies that might actually work, the biological challenges of keeping humans alive for centuries in space, and some genuinely mind-bending solutions that sound like science fiction, but are grounded in real science. Fair warning, some of this is going to hurt your brain. We're talking about warping space-time, building engines powered by black holes, freezing humans for centuries, and potentially uploading our consciousness into machines. So buckle up. Let's figure out if we'll ever become a truly interstellar species. The scale problem. Let's start with the brutal truth. Space is mind-bogglingly, soul-crushingly huge. I know everyone says that, but I don't think most people really grasp just how enormous the distances are. So let's try to wrap our heads around it with a comparison that might actually make sense. Imagine you're standing in New York City, and you want to represent the solar system at a scale you can visualize. If the sun were the size of a basketball sitting in Times Square, Earth would be a peppercorn about 26 meters away, roughly across the street. Jupiter would be a ping pong ball about 135 meters away. And Pluto? That would be another peppercorn about a kilometer away, somewhere in the East Village. Now, at that same scale, where would the nearest star be? Proxima Centauri would be another basketball 6,800 kilometers away, in Los Angeles, on a completely different coast. That's the scale we're dealing with. Let's talk about what light speed actually means, because this is crucial. Light travels at about 300,000 kilometers per second. That's fast enough to circle Earth's equator 7.5 times in 1 second. At that speed, you could get from Earth to the Moon in about 1.3 seconds, to Mars in just a few minutes, to Pluto in about 5.5 hours. But to Proxima Centauri, 4.24 years. And that's if you could somehow travel at the speed of light, which, spoiler alert, you can't. According to Einstein's theory of special relativity, nothing with mass can reach the speed of light. As you accelerate closer to light speed, your mass effectively increases, and it would require infinite energy to actually reach it. The universe basically has a cosmic speed limit built into its very fabric. So we can't go light speed. What about half-light speed? That's still absurdly fast. At that speed, you'd need over 8 years to reach Proxima Centauri. And here's the kicker. We have absolutely no technology, not even theoretical technology, that's close to being viable, that could accelerate a spacecraft to half the speed of light. Our fastest spacecraft ever, the Parker Solar Probe, will eventually reach speeds of about 192 kilometers per second. That sounds fast, right? That's about 0.064% of the speed of light. At that speed, it would take about 6,000 700 years to reach Proxima Centauri. The Voyager 1 probe, launched in 1977, and now the farthest human-made object from Earth, is traveling at about 17 kilometers per second. If it were headed toward Proxima Centauri, which it's not, it would take about 75,000 years to get there. Let that sink in. Our fastest spacecraft that's actually left the solar system would take longer than all of recorded human history to reach the nearest star. But wait, it gets worse. Even if we somehow solve the speed problem, there are other issues. At high speeds, even a fraction of light speed, space, dust, and particles become deadly. A grain of sand hitting a spacecraft traveling at 10% of light speed would impact with the energy of a small bomb. At those velocities, even individual hydrogen atoms become a radiation hazard. And then there's the energy problem. Let's say you want to accelerate a modest spacecraft, maybe 1,000 kilograms to 10% of light speed. The kinetic energy required is astronomical. We're talking about something like 45 trillion joules of energy. For comparison, the largest nuclear bomb ever detonated released about 210 trillion joules. So you'd need about a fifth of the largest nuclear explosion ever, just to accelerate a tiny probe to a tenth of light speed. And that's not even counting the energy needed to slow down when you get there. In space, there's no air resistance. If you accelerate to 10% of light speed, you'll keep going forever, unless you expend the same amount of energy to decelerate. So now you need double the energy. Oh, and you also need to carry fuel for the journey. But fuel has mass. So the more fuel you carry, the more mass you have, the more energy you need to accelerate, which means you need more fuel, which adds more mass. It's called the tyranny of the rocket equation, and it's a real nightmare for space travel. The amount of fuel you need grows exponentially with the speed you want to reach. For interstellar travel at relativistic speeds, the amount of fuel required becomes absurd. We're talking spacecraft that are 99.9% fuel and 0.1% payload. So to recap, space is stupidly big. We can't go light speed. Our current speeds are pathetically slow. The energy requirements are insane. Space debris becomes deadly projectiles at high speeds, and the rocket equation makes everything exponentially harder. Feeling discouraged yet? Don't worry, it gets better, or at least more interesting. The Voyagers, our first steps. Before we talk about future possibilities, let's give credit where it's due. We've already sent missions out of the solar system, 5 of them, in fact. And their story is genuinely inspiring. Voyager 1 and Voyager 2 launched in 1977, during a rare planetary alignment that happens only once every 176 years. This alignment allowed them to use gravitational assists, basically using a planet's gravity as a slingshot to visit multiple outer planets without using much fuel. Voyager 1 visited Jupiter and Saturn. Voyager 2 did something no other spacecraft has done. It visited all 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. The images and data these spacecraft sent back revolutionized our understanding of the outer solar system. But here's what's really amazing. They're still working. Nearly 50 years after launch, both Voyagers are still communicating with Earth, sending back data about interstellar space. They're now over 15 billion miles away. At that distance, radio signals traveling at light speed take over 22 hours to reach Earth. So when engineers send a command to Voyager 1, they wait 22 hours for the signal to get there, then another 22 hours for confirmation. That's a 44-hour round trip for a conversation. And these things are running on 1,970 seconds technology. The computers on board have less computing power than a modern calculator. They're storing data on 8-track tape recorders. The entire computer system has 69.63 kilobytes of memory. Your phone probably has 1 million times more memory than that. Yet somehow, through incredible engineering and creative problem solving, NASA has kept them alive and transmitting. By the 2030 seconds, they'll probably run out of power completely and go silent. But they'll keep drifting through space. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. In 296,000 years, Voyager 2 will pass within about 4.3 light-years of Sirius. They're each carrying a golden record, a kind of time capsule with images, sounds, and music from Earth. The odds of an alien civilization finding one are basically zero, but there's something poetic about it. These silent ambassadors of humanity, drifting through the cosmos long after our civilization might be gone. These missions taught us something important. We can send stuff out of the solar system. We can build machines that survive for decades in the hostile environment of space. We can communicate across billions of miles. But we absolutely cannot use current technology to reach another star system in a human lifetime, or even in multiple human lifetimes. If we're going to become an interstellar species, we need something radically different. Propulsion. The wild ideas. All right, let's talk about how we might actually propel a spacecraft to another star. And I'm going to be upfront. Some of these ideas sound completely insane, but they're all based on real physics. Chemical and nuclear thermal rockets. Chemical rockets are how we've gotten everywhere in space so far. But for interstellar travel, forget it. They're pathetically insufficient. You'd need a spacecraft that's almost entirely fuel, with a tiny payload. And even then, you're not getting anywhere close to relativistic speeds. Nuclear thermal rockets are about twice as efficient, but still nowhere near enough for interstellar travel. Nuclear pulse propulsion, TMET, Project Orion. Now we're getting into the weird stuff. Back in the 1952 and 60s, scientists came up with a wild idea. What if we propelled a spacecraft by detonating nuclear bombs behind it? No, seriously. That was Project Orion. The concept: you have a massive spacecraft with a big pusher plate on the back. You drop a nuclear bomb out the back, it detonates, and the explosion hits the pusher plate. The plate is connected to the spacecraft with shock absorbers, so instead of vaporizing the ship, it accelerates it forward. Then you drop another bomb, and another, and another. It sounds completely bonkers, but the physics actually works. Scientists calculated that an Orion-style spacecraft could potentially reach 5 to 10% of the speed of light. That would get you to Proxima Centauri in 40 to 80 years. Still a lifetime, but at least it's within a human lifetime. Then, the Partial Nuclear Test Ban Treaty of 1963 banned nuclear explosions in space, and Project Orion was shelved. The problems are obvious. You need thousands of nuclear weapons, and good luck getting political approval to launch that into space. But in terms of pure capability, nuclear pulse propulsion is one of the few technologies we could theoretically build right now that might achieve interstellar speeds. Ion drives. Ion propulsion works by ionizing a propellant and using electric fields to accelerate those ions out the back at extremely high speeds. The exhaust velocity is much higher than chemical rockets, which translates to incredible fuel efficiency. But there's a catch. The thrust is tiny. We're talking millinewtons. It's like blowing on a feather. The advantage is that you can run ion drives continuously for years. And over time, that tiny constant acceleration adds up. But even with continuous acceleration for years, you're still not reaching relativistic speeds for interstellar travel. Breakthrough Starshot, laser-pushed light sails. In 2016, a project called Breakthrough Starshot was announced, backed by people like Stephen Hawking. The goal? Send tiny probes to Alpha Centauri within a generation. Here's the concept. You build an enormous array of ground-based lasers with a combined power of about 100 gigawatts, roughly the output of 100 nuclear power plants. These lasers blast a spacecraft that's basically a tiny chip attached to a super lightweight reflective sail. The lasers blast the sail for a few minutes, accelerating it to about 20% of the speed of light. At that speed, the probe could reach Alpha Centauri in about 20 years. Add 4 years for the signal to come back, and we'd get results about 24 years after launch. The physics is solid. The engineering challenges are enormous. Building the most powerful laser array ever constructed, creating sails that won't vaporize, miniaturizing electronics to fit on a chip. Oh, and you can't slow down. At 20% of light speed with no propellant, the probe just screams past the target star system, taking pictures as it goes. But it's achievable with current or near-future technology. Estimates put the cost at around $5 to $10 billion expensive, but less than many space missions we've already done. If Breakthrough Starshot works, we could have close-up photos of planets around Alpha Centauri within our lifetimes. But it's still just a tiny probe. There's no way to scale this up to human-carrying spacecraft with current technology. Fusion rockets. Nuclear fusion is the process that powers the Sunday. If we can make fusion work for power generation, we can potentially make it work for propulsion. A fusion rocket would use fusion reactions to superheat propellant and blast it out the back at a significant fraction of light speed. Various designs have been proposed. Project Daedalus, designed in the 1970 seconds, was a detailed design for an unmanned fusion-powered probe to Barnard's star. The design called for a 2-stage fusion rocket that would reach about 12% of light speed. The spacecraft would have been enormous, 54,000 tons. Mostly fuel. Is this feasible? Maybe. We still haven't achieved sustained, controlled fusion reactions that produce more energy than they consume. Fusion is really, really hard, but we're making progress. Antimatter propulsion. Want the most energy-dense fuel possible? Use antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy. A kilogram of antimatter annihilating with a kilogram of matter would release about 180 petajoules of energy, 3 times more powerful than the largest nuclear bomb ever detonated. An antimatter rocket could, in theory, reach 50% or more of light speed. So what's the catch? Oh boy. First, antimatter doesn't exist naturally in large quantities. We can make it in particle accelerators, but current production costs are something like $25 billion per gram. We'd need kilograms for an interstellar mission. Second, storing antimatter is a nightmare. If antimatter touches any regular matter, it annihilates instantly. You have to contain it using magnetic fields in a perfect vacuum. CERN produces about 1 to 10 nanograms of antimatter per year. At that rate, we'd need billions of years to produce enough. Antimatter propulsion is probably centuries away from being practical, but the physics is sound. Bussard ramjet. Here's a wild idea from 1960. What if your spacecraft could collect fuel as it travels? Space isn't completely empty. Even between stars, there's about 1 hydrogen atom per cubic centimeter. A Bussard ramjet would use enormous magnetic fields to scoop up interstellar hydrogen as it flies. Then, it would use fusion reactions to propel the spacecraft forward. The brilliant part: you don't need to carry fuel. In theory, you could keep accelerating indefinitely. The problems: you need to travel pretty fast already to scoop up enough hydrogen. Creating magnetic fields hundreds of kilometers across would require enormous energy, and the drag from scooping might slow you down more than the thrust speeds you up. The math on whether this would even work is still debated. Time dilation, XP. The relativistic advantage. At relativistic speeds, say, more than 10% of light speed, Einstein's special relativity kicks in hard. Time dilation becomes significant. From the perspective of people on the spacecraft, time passes more slowly relative to people back on Earth. At 99% of light speed, for every year that passes on the spacecraft, about 2.3 years pass on Earth. At 99.9%, The factor is about 22. This could actually be an advantage. A crew traveling at 99% of light speed to a star 100 light-years away would experience the journey, taking about 14 years from their perspective, while over 100 years pass on Earth. But reaching those speeds requires enormous amounts of energy, and the faster you go, the more dangerous space dust becomes. The biological nightmare. Okay, so let's say we solve the propulsion problem. We still have another massive problem: keeping humans alive for the journey. Even at relativistic speeds, interstellar journeys take decades at minimum, more realistically, centuries. And humans? We're fragile. Radiation, the silent killer. Space is flooded with radiation. Cosmic rays, solar particles, and at high speeds, even interstellar particles, become deadly radiation. On Earth, we're protected by our atmosphere and magnetic field. In space, you're exposed. Radiation damages DNA, causes cancer, degrades your nervous system. For an interstellar journey lasting decades or centuries, this is critical. You need shielding. Water is good at stopping radiation, but it's heavy. Polyethylene works, but again, mass is your enemy. Some designs propose using the spacecraft's fuel and supplies as shielding. Magnetic fields could deflect charged particles, but creating one strong enough requires a lot of power. There's no perfect solution. Any interstellar mission would accept some radiation exposure and elevated cancer risk. Life support. The closed-loop problem. Humans need oxygen, water, and food. On a journey lasting decades or centuries, you can't just carry it all. The mass would be prohibitive. You need a closed-loop life support system. That means recycling everything. The International Space Station recycles about 90% of its water, but that remaining 10% is lost, and the ISS is regularly resupplied. For an interstellar mission, there are no resupply runs. You need to get closer to 100% recycling. That probably means biological systems, plants, algae, bacteria converting waste back into usable resources. Biosphere 2 Inches Arizona tried to create a self-sustaining, closed ecosystem. It didn't go great. Oxygen levels dropped. Carbon dioxide spiked. Turns out, balancing a closed ecosystem is really hard. For an interstellar ship, you'd probably combine mechanical and biological systems. But these are complex, and failures could be catastrophic. Gravity. Use it or lose it. In microgravity, the human body deteriorates. Bones lose density at about 1 to 2% per month. Muscles atrophy. The cardiovascular system weakens. For a journey lasting decades, microgravity isn't viable. You need artificial gravity. The classic solution is a rotating spacecraft. Spin it, and centrifugal force creates the sensation of gravity. The problem is size. To create comfortable artificial gravity without making people sick from Coriolis effects, you need a big radius, probably at least 100 meters, ideally more. That means your spacecraft is huge. And huge means massive, which makes acceleration harder. The multi-generation problem. Even at relativistic speeds, the nearest interesting star systems are decades away. For more distant targets, we're talking centuries. No human lives that long. So you need a generation ship, a spacecraft where multiple generations are born, live, and die during the journey. This creates enormous social and psychological challenges.